Now let's focus our attention to isothermal reactor design, in particular tubular reactors, and we will use the PFR reactor or the plug flow reactor as our example. For the case of a tubular reactor, remember that typically we have gas phase reaction happening inside those type of reactor. So if we want to model a plug flow reactor, we assume, right, that there's no dispersion or that the reactants and the mixture, right, is really well mixed, therefore is turbulent. We may see later examples with a laminar flow and moments or conditions that we need to take into consideration dispersion in the reactor. But right now we're assuming that there's no dispersions. So the other thing is that we assume that there are no radial gradients for temperature, concentration, the reaction rate, and the velocity. So that those criteria allow us to model this reactor as a plug flow reactor. From the mole balance, we get the differential form for the design equation for a flow reactor. Make sure that now that we have and we know that that there could be pressure drop in a reactor, that you start always with the derivation of the mole balance and kind of stop on the differential form to decide if there's pressure drop or not. Okay, so in this particular case, there's no pressure drop. So the same method applies when you are having heat exchange in the reactor. So we will get back again to this equation when we have those conditions. So just to simplify the derivation and to just analyze a plug flow reactor and see how the conversion relates with the damp color number for this particular reactor, we're going to assume then that the pressure drop equals to 0. Give us that the volume can be related by the following integral form for plug flow design equation. Okay, so now let's consider a second order reaction. So for a gas phase reaction, we can define the volumetric flow rate in terms of conversion, the pressure drop, and the change in temperature as follow. Remember that epsilon, the term epsilon is actually involves the molar fraction initially present for species A times delta, and delta is obtained from the stoichiometry of the reaction. For this particular example, we know, or it is assumed, that the temperature is constant. Okay, so that means that this term is equals to 1, and also that there's no pressure involved. However, remember that if this is not true, you need to start with this formula, this equation, and then make the appropriate assumptions depending on the statement. So now we get from stoichiometry the definition of the concentration at the exit of the reactor. We are substituting the definition for FA and the definition for the volumetric flow rate, right, for gas phase reaction. Then after we simplify, we end up having this expression involving the initial concentration of the reactant and the conversion for the reactant. Combining and substituting this on the definition, right, for the volume obtained from the mole balance, we get this expression for it. Now we have to group together terms that are constant. We get that the volume integral form, right, looks like this. And we are ready at this point to do integration. I'm not gonna do the whole 9 yards integration, but we did in class the algebraic manipulation to simplify the integral, right, in such a way that you can use available integral tables. So if you cannot find this integral solution on a table, you need to manipulate it in order to get in order to solve it. Fogler does have an appendix in the bag in Appendix A that does contain the solution for this integral. So I'm just going to add it here. Once again, you will have the integrals in your exam. However, you need to know how to use it in case that you don't have exactly the solution. So you need to do some of the algebra behind it to get to those. So I know that you are waiting for this. So at home, hashtag I love ChemE, try to get to a volume solution where you have a reaction that is liquid phase. Okay, that means that you're going to be assuming that the volumetric flow rate is constant. Remember, the steps on the method are the same, so make sure that you know where are the changes happening. Okay, so review this and we can discuss it on the next class. So you have a homework. For the second case, let's consider the epsilon smaller than 0 and delta smaller than 0. We can notice if you look at the terms, right, that they're going to be affected, especially the epsilon, as the volumetric flow rate decreases. The volumetric flow rate decreases as the conversion increases. So you can visualize this better. Let's consider this reaction, right, of 2A going to B, where you're putting into the reactor pure A, and A is the limiting reactant. Therefore, we can rewrite the equation as follows. If we calculate the epsilon, right, epsilon equals at A0 delta equals to 1, 1.5 minus 1, right, that will be the delta, equals to minus 0.5. Remember that we mentioned that A is pure, therefore the molar fraction equals to 1. If we put this back into the equation, we end up having this expression for the volumetric flow rate. So as you can notice, the gas molecules in this particular case will spend more time in the reactor than they would if the flow rate were constant. Okay, so you can see big difference between this relationship and this this relationship, right, where you have the volumetric flow rate constant throughout the whole reactor. So one of the factors that are affected here will be the constant tau, the space-time tau, because it does depend on the volumetric flow rate, right? It depends on the volume, so that parameter will be affected too. Let's now look at the graph. Right, we know that we're going to divide as part of as the y-axis. We can have the volumetric flow rate over the initial volumetric flow rate. So if I need to graph the 1 minus 0.5x in this particular graph as a dependence with the like a profile with the volume of the reactor, we end up having something like this, okay, where the limit of this particular graph will be equal to 0.5, okay? So remember, in this case, delta is less than 0 and epsilon is, in this particular case, equals to minus 1/2. So finally, if now we have the condition where epsilon is larger than 0 and delta is larger than 0, we are looking at a reaction that is actually increasing the total number of mole after the products are produced. Okay, so for this particular case, we have epsilon being equal to 1. So if we go back to the volumetric flow rate equation, we end up having this expression, okay? And here you can notice, right? That as the volumetric flow rate increases, the volumetric flow rate will be increasing as the conversion will be increasing too. So here in this case, the molecules or the reactants will be spending less time in the reactor than they would if the volumetric flow rate were constant. Okay, they're typically we are going to be traveling, faster than the other examples that we have seen. Let's go to our diagram here. So we're talking about a graph, right, that will have this as a limit. We know that this is 1, therefore this should be 2 because you are adding to it. So let me see if I'm looking at this. 1, 2, yeah, it looks like it's the same, so I'm just gonna, it's kind of more than that. Okay, here, 2. What I'm doing is that I know that this number should be larger than the one in the bottom, so I'm just making sure that. And that limit for, right, curve will be this. So when delta larger than 0, in this particular case, epsilon equals to 1. Okay. So, understanding how the volumetric flow rate varies in the volume of the reactor is very important, especially because we are always dealing with different type of reactions. So you have to, at the beginning of the statement, be very, very aware of all those critical aspects, right? Who is the limiting reactant? If the reaction is pure or not, if we have an increase of the total number of moles after the reactants, after the products are produced. So you have to keep track of that. So that means that you have to be aware that there will be substantial changes on the definition of the volumetric flow rate, even that is the same reactor, right? You may have different times related, space-time related to it. You may have different variations in the concentration profile or the flow rate profile.